So last we left off, I believe we were talking about we had talked about formal charges, right? Yes, no, maybe?
Yeah.
Okay. And I believe this is the slide. Okay. So I believe I left you guys here and I said, okay, you guys got to be ready to answer this one. So do you guys want to go through it real quick together? Since there's only 5 of us.
Yes, could we go over them?
Yes, we can. So how many electrons does carbon have? Let's start off with carbon monoxide. How many valence electrons does carbon have?
4.
So it's 4 valence electrons. And oxygen?
6.
And it has 6 valence electrons. So altogether we have 10 electrons to work with. So okay. So we want it so that both of them have 8 around them. So the only way that we can make this work is if we this guy put it in here and take this guy, put it in there. So then we'll get okay. So if we're calculating the formal charge for this guy, so for carbon, formal charges is what again?
The valence electron of the atom minus the
number of lone pairs.
Minus.
bonds minus
Atom minus lone pair electrons minus bonds. Okay, so for carbon, how many the valence electrons was 4, right? How many lone pair electrons do we have on our carbon atom? There's only 3 of you guys here, so one of you guys have to say something.
What did you say?
How many lone pair electrons do we have around the carbon?
2.
How many bonds?
3.
Okay, so we have our 3 bonds and we have our 2 lone pair electrons. So then that's going to give us a value of -1. Okay, for the oxygen, how many valence electrons?
6.
How many lone pair electrons?
2.
And then how many bonds?
3.
Okay, so then that's going to give me a positive. Okay, so unfortunately, this is the best that we can do. We can't do any better. So we have to settle. Right? It's not ideal because oxygen really doesn't like to be positive and carbon is less electronegative. So, you know, but that's the best we can do. This also kind of tells us that carbon monoxide is kind of reactive, right? It lacks that complete stability. So it's going to be willing to react. Okay, so what about the nitrogen chloride? So Nitrogen has how many valence electrons?
5.
The chlorine has how many?
7.
So times 3. So that's 21 plus 5. So 26. Who's going to be the center atom?
Nitrogen.
That is correct. Nitrogen is going to be the center atom. So 1, 2, 3, 4, 5. So we have chlorine, 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 which has 7. That's 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, so we want to set it up so they all have 8 around them. So we're going to go ahead and move this guy up here and this guy up here. So we're going to end up with okay. So if we do formal charges for the chlorine, so how many valence electrons again does chlorine have?
7.
How many lone pair electrons surrounding the chlorine?
6.
6.
And how many bonds?
1.
Well, that's equal to 0. They're all the same. And then nitrogen, we have 5 valence electrons. How many lone pair? And then how many bonds? Was that the Al answering?
Mm.
So that's 0. Okay, piece of cake. Yeah, no, maybe.
Yeah.
Okay,
Yes.
and then we have Br, right? Br has 7 valence electrons. Cl, which we already know from, also has 7. 7 times 3 is 21. So we have 28 electrons to work with. I'm going to erase this guy. So who's going to be the center atom?
Bromine.
Okay. So you guys got this. We're just beating a dead horse now. Okay, so we have Cl here. Cl here. And Cl here. Okay, so we can form one bond here. We have an extra electron. We can form one bond here. So these 2 electrons we're going to stick here. And let me erase. Make it pretty. Okay. So if we do for Br, the formal charge, it has 7 valence electrons. How many lone pair?
4.
4 lone pair. And then how many bonds?
3.
3.
It sounded like the kid in the background was screaming 4.
It did.
I'm like, man, he's already learning it. So I think we beat a dead horse. Oh, that's 0, right? Not 7. And then the CL is going to be the same as it was earlier. So it's 7 minus 6 minus 1. So that's 0 as well. So perfect. These guys are happy. Piece of cake?
Yeah.
Good.
Yes.
Okay. Okay. Oops. Got carried away. Okay. So here we have thiocyanate and nitrous oxide. Okay, so thiocyanate, who's going to be the center atom?
Carbon.
Carbon.
Yeah, carbon.
Okay. And carbon has 4 electrons. So let's see, 4. Nitrogen has how many valence electrons?
5.
I know you guys get tired of saying it. I'm going to keep asking just to make sure. And sulfur has how many?
6.
And then we have this minus sign. What does that mean?
Add an electron.
Add an electron. Okay, so we're going to add it here. Okay, so to make these guys so that everybody has 8 around them, we can do this.
Dr. Henry.
Yes.
May I ask, why did he put the extra electron on the nitrogen?
Because sulfur has 6 around it.
Mm.
And then we know that carbon, technically we could have stuck it in the middle. Nitrogen has 5. So we know it has to have an even number. So I just went ahead and put it around the nitrogen.
Okay.
So because the electrons are mobile. We'll talk about that in a minute. So they're really moving around. So even though I may put it there, it's going to move around to the right spot anyway. So. Okay. Or I should say, it's going to circle the right atom anyway. Okay, so here's one possibility. All right. Another possibility that we could have is I should put, forgot my bracket. Minus. Minus. And the other possibility is, oops. Okay. Good, bad, ugly. Okay, so how do I know which one is going to be the best?
Formal charging.
The formal charges. Okay, so the nitrogen here, 5 valence electrons minus 4 lone pairs, minus 2 bonds. So that's going to be a -1. Carbon, we have 4 valence electrons minus no lone pairs, so 0, minus 4 bonds. That's going to be 0. And then we have sulfur, which has 6 valence electrons, minus 4 lone pairs, minus 2 bonds. So that's going to equal 0. Okay, so if we look at this nitrogen, we have 5 minus 6 minus 1. That equals -2. Carbon is going to be 0. And sulfur is going to be, sorry, just had a momentary brain fart, -3. So then that is +1. Oops, this is bad. And the last option, we have N. So we have 5 minus 2 minus 3. So that equals 0. We have C, that's going to be equal to 0. Whoops. That's 4. And then we have S, where it's 6 minus 6 minus 1 equals -1. Okay, so which one is going to be the preferred structure? A, B, or C?
A,
A, why?
because the -1 is on the one with the most or more electron activity.
That is correct. So A would be the correct answer. Good job. Okay, so here we have this guy. Oops. N. Or we could have the same situation where we have a triple bond, single bond, or the other way around. Oops. Okay, so if we look at our formal charges, this first N, this N over here, it's 5 minus how many lone pair? 12, 17, 9,
4 for nitrogen.
4, okay, minus how many bonds?
2.
that equals -1. And then we have the nitrogen in the middle. Oops. So then that's 5 minus 0 minus 4, which equals +1. And then we have the oxygen here, which is 6 minus 4 minus 2, which equals 0. Okay, under this circumstance, we have that first in, so then that's 5 minus 2 minus 3, which equals 0. The middle, which is 5 minus 0 minus 4, which is +1. And then we have the oxygen, which is 6 minus 6 minus 1, which is -1. And then the last possibility is for this guy, which is we have 5 minus 6 minus 1, which equals -2. We have nitrogen in the middle, which is going to be 5 minus 0 minus 4, which equals 0. And then we have oxygen, which is going to be 6 minus 2 minus 3. So that's going to be a +1. I mean, wait a minute. 2, 4, 6, 6. Oh, this guy is a +1. Not. You guys aren't going to tell me that my math is bad? Now let me sit here. Okay. So, which one is preferred?
B.
A, B, or C? I heard somebody say it.
B.
B? Yes, so B is preferred. And that, again, is because oxygen is more electronegative, so it's going to want to have the negative. Piece of cake?
Yeah.
Yeah.
Good. Excellent. Okay, let's go clear. Okay, so if we have nitrate, the nitrite ion, we have NO2 minus. Okay, center atom is going to be who? Again?
N.
Okay. And we have 5 valence electrons. Oxygen has 6. 6 times 2. It's 12, plus the one that we're adding because of the negative charge, 1. So that's 18. Okay, so how can I make it so that everybody's happy? have 8 around them.
Do a single bond on each side.
Single bond on each side. So if we do that,
Use electrons from nitrogen.
so we're going to take this guy, put it over. We're going to move that one directly over. So we'll go Is everybody happy?
Oh, shoot, no.
Okay, so what do we need to do?
Do a double bond on one of the oxygens.
Okay, so we'll take these guys and move them over here. So we'll end up with double bond. Okay, so that one works. Is there any other possibility? Okay, so this is our possibility, right? So the other possibility is not really a possibility. It's called what we call a resonant structure. Okay, so in this case, we have the double bond that's kind of shifting over and going from one side to the other. So this side will end up with a double bond on one part. This side will end up on a double bond on the other, right? So I told you that the electrons are always orbiting, they're always moving, right? So since the electrons are always moving, so these electrons are going to be moving from this nitrogen over to this oxygen, and so on and so forth, right? So if we do like formal charges, this oxygen here is going to have a 0 formal charge. This nitrogen is always going to have 5. This guy is going to have a 0 formal charge as well. And this guy is going to have a -1 charge, formal charge. So on this time, this guy is going to have a -1. This guy's going to have a 0. This guy's going to have a 0. So what's happening is that both of these structures kind of exist. So what happens is that the electron is moving from one oxygen to the other oxygen, one oxygen to the other oxygen, one oxygen to the other oxygen, right? And it's going to be more on the oxygens than it is going to be on the nitrogens. Okay, so a resonant structure is just when you have that electron that is going to be resonating between the other alike molecule. So in the case, oxygen. Does that make sense? And since both oxygens have the same pool, right? Since they both have the exact same pool, then, you know, neither of them are preferred more than the other. So it's going to spend about equal time on both oxygens. Are you with me? I would say you guys look like you're confused, but I can't see anybody's face.
I kind of understand.
What about you?
Yeah.
Kind of understand?
Yeah, kind of.
Okay. Okay. So let's see. Okay, so this is the way that resonant structures are kind of drawn. So you can kind of see the dashed line between here. So that basically means that the electron is being oscillating between this guy and that guy. Okay, so it's going between these two oxygens. Okay, so show the possibility of resonant structures for carbon carbonate, the carbonate ion. Okay, do you guys want to do this? You have time to do it alone? You guys want to get intimate with each other? Okay, so I'm going to put you guys in breakout rooms. And then I'll see you in a breakout room. I'll see you guys back here in 5 minutes. Think you'll have it in 5?
Yeah.
I know it's not 15 problems, right? Okay, room is open.
Do I join the room, Dr. Henry?
It's up to you. You can't give them the answer.
I'll just stay here then.
Uh-huh.
Yeah, because they'll ask me, and then I will.
You'll buckle, right?
Yes, I will. I had a question about, I know this is like further along, but during fall semester, would you happen to, sorry, my video went off. Would you happen to know if the classes will be like in person or not?
Yes. Yes, they will be in person.
Okay.
We're going to have to modify them a little bit. We may do hybrids, like part of the lectures are going to be face-to-face and part of them are going to be online.
Okay.
But labs are all going to be face-to-face. Thank God.
Okay, yeah, because I was looking over the organic chemistry class, and
Yeah,
I noticed that they have like lecture in person. So I was like, is it happening? So I wanted to ask.
yeah. It's planning to be in person, but we may have to do some finagling since I'm going to be technically teaching at 2 sites, NDC and here, and at Kalinga.
Okay.
So,
All right.
I am exhausted. Whew.
Yeah, I'm pretty sure you start your day early.
Yeah, way too early. So how are your classes? Are you taking any classes this semester?
Yeah, I'm taking the second half of physics and biology.
How's that going?
It's going. I feel like a lot of my time goes into physics.
Yeah.
Because the professor's very harsh when it comes to the labs. He wants it a specific way. So I have to make sure that I do it that specific way.
Yeah.
But it's going. I'm passing. I mean, I have A's on both classes, but those are like very well deserved A's.
Okay.
Yeah.
Good.
Yeah, but
I like hearing it.
yeah, I feel like school is just like the time that you put in is like the reward.
Yeah.
And if you don't put the time in, obviously you're not going to see anything. But these classes like chemistry, physics, biology, they're hard, yes, but like if you don't spend time in those, like if you don't spend time studying, you're not going to pass, in my opinion. Like
Yeah.
you're not gonna pass the class. Going to the lecture is not enough, or watching the lecture is not enough.
I agree.
Yeah.
I agree.
Yeah, but I
and that's the thing that it's really hard for a lot of students to understand, you know, that you need to do more than just watch the lecture.
Right.
Yep. Hey, you guys are back. We lost somebody. Oh, no, we didn't. That last one is me. So do you guys have answers for me?
Yeah.
Excellent. So you guys can write it on the board. Okay, so that's one of the resonance structures. So what will be the other?
Do you want us to draw all three?
Yeah. So was there a big debate about this, or was it really easy to whip out?
It was actually easier than I thought it would be.
Yeah. And Mauricio, you gonna do the last one, or Alex?
I can't write on the board.
I know, but you can dictate to me. I'll be your secretary.
Okay, let's go.
Okay.
So carbon is in the middle.
Okay.
Then 3 oxygens around it.
Okay.
The oxygen on the right hand side has a double bond with the carbon.
Okay.
And it has 2 pair electrons that are non-bonding.
Okay.
The other 2 oxygens just have a single bond and have 6 electrons, which is 3 pairs.
Okay.
And then the brackets. And -2 on the upper hand side.
Okay. So that's it. These are your resonance structures. And the arrows just to let us know that they're resonance structures, to kind of remind us. Okay. Questions, concerns, catch? Piece of cake, right?
So what is
Yes.
like what is that word called? How do you say it?
Resonance. Resonance. So resonance basically means that the electrons is kind of resonating between elements that are the same, that have the same electronegativity. So in other words, you're gonna have a double bond here. Well, this double bond could actually be here. And then this double bond could be there. Because electrons are constantly, they're orbiting around these atoms. And because the oxygen has a stronger electronegativity than the carbon, it always is going to pull that electron. So occasionally it'll be pulling, this guy's going to be pulling those both sets to share. And then occasionally this guy's going to be pulling both sets to share. And then occasionally this guy's going to be pulling both sets to share. And so each set is basically going to get that electron 1/3 of the time in this case. Does that make sense? Because all of the oxygens have the same electronegativity. So they're going to be pulling the same. So the probability is going to be 1/3 of the time, you're going to have that double bond here. 1/3 of the time, you're going to have the double bond here. And 1/3 of the time, you're going to have the double bond there. Does that make sense? Yes, no, maybe?
Yeah.
Alex?
She's not here.
Did she leave?
It looks.
Oh, Alberto, did you just come in?
Yeah, I did.
Okay. So what? You and Alex can't be in the same room at the same time, so she has to leave?
I guess so.
Okay. Because wasn't she was the one that answered asked the question, right? Okay. Well, I
Yeah.
guess so. Okay. So the next thing that we're going to talk about is the strength of ionic and covalent bonds. So here you're going to basically be learning about the energy that's involved in forming and breaking bonds. Okay, and we're going to talk about ionic and covalent. So we're going to start with the covalent part. So if we have these two atoms that are interacting, they're forming a covalent bond with each other, X and Y. So the process of breaking those bonds require energy. There's going to be so much energy that it's going to cost us to sit there and dissociate your X and your Y. And that's going to be calculated as your dissociation energy or your bond dissociation energy. And it's also going to be equal to the enthalpy. Okay. So you guys should be kind of familiar with enthalpy from the last time that we talked. Well, you can never get away from energy. So we've got to think about energy all the time. So in the case of, this is supposed to be H2. Okay. So if we're breaking down H2, and then we're just going to make the hydrogen a single hydrogen atom gas. So we'll have two of those. So the energy to dissociate that is 436 kilojoules per mole. Okay. So per mole of that particular of H2. Okay. So there's a table, you basically have tables that describes the energy that it takes to break a bond, a single bond. So in the case of carbon and hydrogen, I'm going to kind of skip ahead. We have this nice, beautiful table that shows a bond between carbon and hydrogen. And that energy is 415 for one bond of carbon and hydrogen. Well, methane has 4 bonds of carbon and hydrogen. So the way that we can calculate the energy that it would cost to dissociate that is each of those are 415. So if we go 415 times 4, because that would give me my breaking of all 4 bonds. So then 4 times 415, that will be 1,660. You get that?
Yeah.
So The energy for dissociation of just this molecule alone is 1,460. Each bond, each dissociation of each individual bond is 415. Okay. So now this value is considered to be estimate because usually it takes a little more energy to break the very first bond than it takes for like the second and the third. And so it gives you basically the average of that. Does that make sense? Okay. So here we can kind of see the energy that's associated with breaking each of the different bonds, right? And you can see, let's say we have this guy has a double bond, this guy has a triple bond. So going from a double bond to a triple bond, you're going to get an increase. It's going to take more energy to break the triple bond than it will take to break the double bond. And then if we went a single bond, let's see, where's my CN? So if you go down here, we have CN down here, 290 compared to our double bond. So a single bond is easier to break than a double bond. So does that make sense?
Yeah.
Okay. So the other thing is that if we compare a single to a double to a triple, so the bond length, the distance between those two atoms gets smaller the more bonds you have. So a single bond is further apart than a double bond, and a double bond is further apart than a triple bond. Okay. And so in other words, these guys are pulling each other tighter with the more bonds that they have between them, or the more electrons that they're sharing between them. Okay, does that make sense too?
Yes.
Good. Okay, so then it's getting real easy. So the way that we would calculate the change in enthalpy would be delta H is equal to the summation of all the broken bonds minus the summation of all the bonds that are formed. Okay. So in this case, we're going to break this bond, we're going to break this bond, and we're going to reform this bond, right? So the way that that's going to work is, so we have the dissociation energy associated with just breaking that bond, dissociation energy that's associated with breaking up that bond, and then it'll be 2 times the dissociation energy of this guy, right? And we're going to use a negative value because that means that we're forming. Okay, so the energy that's required to break the hydrogen was 436. The chlorine is 243. So we'll add those two together, and then we'll subtract the energy that is required to form the HCl. And again, all of this is going to be provided to you on a table, so you'll have a table to sit there and look at. Okay, you guys can see all of them, except for some reason I forgot to put chlorine up here. I'll have to fix that. The chlorine bond. Okay. Pretty simple.
Is that chart in the book?
Yes, this chart is in the book. Yep. And it'll also be available for your exam. Okay.
Okay.
Okay. So, and this is a typo, I apologize. So the enthalpy of formation would be for 2, this would be for 2 moles of HCl. But if we want it for a single mole of HCl, we would divide it by 2. So each one would be 92.307, okay? For one mole of that. So. Questions, concerns, Cash? Pretty simple? Okay, so let's do this then. Let's calculate the enthalpy of formation for let's do something hard. Let's do, we'll go. So that would be 1/2. Okay. So let's go back to that table. Come on. May work. Okay. So if we have this chemical equation up at the top, let me kind of draw this Lewis structure of this guy. Okay, so how will we go about calculating it?
The H2 bond.
Okay, so that's 436, and it's
Times 2.
times 2. Okay, let's do it like that. Plus.
Would you get the CH or the HC bond? Or
So in this case, it's just carbon alone. So in that case, there's no bond to have, so it'll be a 0 value for carbon.
okay.
So that's like a give me. Okay.
And then the O2 bond.
Okay, so then the O2 bond. So right here, so 140.
Divided by 2.
Divided by 2. Okay. Okay. And then what about this guy? The formation. So we're going to subtract it. And which bonds do we have?
C and H.
So we have how many C and H's?
3 H's.
So we'll go 3 times 415. Plus CNO. Which is 350. Plus OH. What is OH?
464.
So if we do that math, I don't have my calculator.
I got negative 1,117.
Okay. Okay, so that would be kilojoules per mole of methanol. Piece of cake?
Yes.
Okay. Ugh. Okay, so let's go with so if we were doing the calculations for these guys, you guys will be able to do it, no problem. Yeah, no, maybe?
Use when we added. Oh, from looking at the equation instead of the structure,
Uh-huh.
I got confused on like adding the C and O bond.
Oh, really?
But then when I saw the structure, I see that it's connected. So it's, yeah.
Alexandra said no.
Who said no?
Alejandra or Alexandra?
Yeah, I'm still kind of lost.
Okay.
I don't know. For some reason, every time I talk on my Zoom, I don't know, so my Wi-Fi kind of sucks. Like on all my classes, it'll log me out, so that's why I'm scared to talk.
Okay. Okay, so let's do this guy here. So in this case, we have a triple bond, right? Triple bond between the C and the O. Okay, so if we go back to the table.
On the test, will we have the table?
Yeah, the table's going to be provided. So triple bond between the C and the O is, I'm just going to write the chemical equation up here so we can start it. If I write it up top, you guys can see it.
Yes.
Let's see, what was it? CO. Yeah, I can't remember what it was. Old age, you know. Got it.
So on the test, Dr. Henry, would you only have like the chemical equation, and then from there we would have to draw the structure and whatnot?
That's right.
Okay.
And then you're going to end up with CH3OH. Okay, so we need two of these, and then everything is balanced. Okay, let's see. Okay, so we know that this guy's a triple bond. If we draw the structure, so that's C triple bond O. Okay, so we'll go C triple bond O. So we have 1080 plus, so Alexandria, we have a bond between hydrogen. So it's a single bond between a hydrogen and a hydrogen. So what is the energy for that? 436. And so there's two of them. So we want to multiply that times 2.
Okay.
2 times 436. And then we're going to subtract what's on the product side. Okay, so
you're always going to subtract what's on the product side?
That's correct.
Okay.
Yeah. So here we have multiple. We draw the structure, we have a carbon, hydrogen, hydrogen, and a hydrogen. And then we have OH. Okay, so how many carbon hydrogen bonds do we have?
3.
So it'll be 3 times 415 plus how many bonds between carbon and oxygen?
1.
1. So then we find that's a single bond between carbon and oxygen. So then that's 350. Plus a single bond between oxygen and hydrogen. And that's what?
What is it?
Right here?
Oh, it doesn't matter if it's the other way around?
No, it doesn't matter. It's still, it's represented the same value.
Okay, so yeah, 464.
464. Okay, ran out of room. Okay. And
So
then you just
solve it.
Yep, then we just solve it. So, 436 times 2. So this guy is 872. So we have 14 times 3. This guy is 1245 plus 350 plus 490. Okay. So plus 350 plus 4. So your delta H is going to be 107 kilojoules per mole. That's kJ. Okay. Piece of cake?
Yeah. I get it now.
Okay, good. Okay.
But we have to memorize like the bonds, right?
Oh, the bond energy? No, what you need to know is be able to draw the Lewis structure, right? Because that's going to help you.
No, like. Mhm.
So you're asking me, you're not going to need to memorize this table. No. But what you're
No,
going to
but
need to.
We need the energy thing. You know what I mean?
What do you mean?
Like the bonds. Like we just have to know what bonds they are.
Yeah. Yeah. And the way that you do that is by drawing the Lewis structure of them. Right?
Yeah. Uh-huh.
So that's the same thing down here. So I'm not going to do this one. I'm going to save this one because you may see it. Like on a practice test or something. Okay, so let's talk about lattice energy. Okay, so lattice energy is basically the energy that is when two ions are attracted to each other, the energy that of attraction. So it just basically measures the strength of attraction. Okay. And so the way that we calculate that, we say that our delta H lattice is going to be equal to, C is going to be a constant depending on the crystal type. And that's usually going to be given to you. And then Z is going to be the charge on the ions. And then R is going to be the inner ionic distance between the two. So it's basically just the radii of each of the different ions. Okay. So let's say we're doing magnesium oxide. Okay, so again, we're going to leave C as C because C is just going to be a constant, whatever it is for that structure. So what is the charge on magnesium? Anyone? So in magnesium oxide, what is going to be the charge on magnesium?
+2.
That's right, +2. Okay, so the Z value here is going to be 2. The Z plus is going to be 2. And then what about the charge on oxygen?
-2.
Okay, so then we also just use 2. So it's just going to be the absolute value on it. So 2 times 2 times C over R naught. The way that you would calculate R naught, you can use, and this is going to be a rough estimate, P table. Where is it? Okay, so we have our calculated radius. So we'll go to magnesium. So it's going to be a 145 picometers. And then oxygen. Where is it? Right there. 48 picometers. We add them together. So we get what? 193 picometers. And so that's what we use for our R naught. So we'll end up 4 over 193 times C. And then that's going to give us our delta H for that ion. Piece of cake? Yes, no, maybe?
Maybe.
Maybe. Okay. So if I have, let's say we have calcium chloride. So what are my Z's?
+2 for calcium.
Okay, so we're going to go C times 2. And then for the chloride,
1.
so times 1. Okay, and then we would just get the R from P table. So that's 79. Plus the calcium. 194.
Oh, that's how you got that.
Yep. And so then we have that together. So that's 3, 6. So it'll be 2C times 263. Okay. Piece of cake?
Yeah. For like, if we're gonna do this on the test, will we be able to get the
value for C?
the radius? Huh?
Yeah. Yeah. I'll let, I'm gonna try to get a table together for you guys just for this particular problem. Or you're gonna have access to P table. So okay. So the Born-Haber cycle. Okay, so for the Born-Haber cycle, it's okay, so it's a lot of steps, but we'll kind of go through it all together. So we can actually use the enthalpy of various things, right? So for instance, this one is the enthalpy of going from a solid to a gas, right? So we're changing. This is cesium that is going to be reacting with fluorine or fluorine gas. So the first step would be going from a solid to a gas. And so this is the delta H that is for that state change. So it takes 76.5 kilojoules per mole to change cesium into a gaseous cesium. Okay, now once it's in a gas, then we can use the electron affinity. I mean, not the electron affinity, the ionization energy. So that's what the IE stands for. Okay, so it's going to be the ionization energy added on to the ionization energy added on to the, I can't even think straight right now, added on to the state, the enthalpy of the state change from solid to a gas. And then we have our dissociation energy for dissociating just that the fluorine. Okay, so it's 1/2 the dissociation energy. So then we get cesium plus the fluorine gas. Okay, so now here, we use the electron affinity. Electron affinity is basically the desire to have an electron added. So we use the electron affinity of the fluorine. And then that means that the fluorine picks up that electron that cesium had dropped off earlier. Okay, and then we calculate the ionization energy or the lattice energy for that formation. So if you take the difference between these guys and these guys, then you're going to get this as your total delta H of formation for that reaction. So if you're saying starting from here, going all the way to this forming. Does that make sense? Yes, no, maybe? Okay, perfect. That means that everybody understands it, and I'll put it on the exam.
No.
So you guys got to speak up or hold your peace. So let's talk about where you find these values. So if we're going from cesium to cesium gas, this guy is going to be found in your appendix, in your textbook, or it's going to be given to you on a table, right? Because you're just going from a state change. So you're going from a solid to a gas. So we go this plus the ionization energy. So there's tables that have it, but also P table has it. I'll actually print out P table's ionization energy so you can use it. The table that we used earlier has the dissociation energy for fluorine, because that's the next step, right? So we're going to dissociate fluorine, so we have just a single fluorine that's able to react. So this is going to be this plus this, and then this gives us this forming. And so now fluorine is ready to accept that electron that this guy had hanging around. So if fluorine accepts that electron, that's going to be your electron affinity energy. And so we can find that on P table as well. And I'll show you where it's at in a second. And so we'll go ahead and we'll add that to it. It already has that negative value, so it's accounted for it being negative. And then we calculate the lattice energy. Okay, so in this case, it's going to be minus the lattice energy. Because the lattice energy is, if we looked at that equation, it represents the dissociation of the two. So we want minus the lattice energy, so that means you'd have the formation of the two. Does that make sense? Let me point it out. Let me go back. Oops, wrong way. Okay, so here. So you look how the equation is written. So the lattice energy is going to be the breaking down of the two, not the formation. So your metal and your non-metal being broken down. So your ionic compound being broken down into just its ionic components. So that's the lattice energy, right? So it becomes negative. If we make it a negative, that means that we're going the other way. So we're going from M, that should be M plus X minus to make MX. And so that would be minus delta H lattice, because you're flipping the equation. Does that make sense?
Yeah.
Kind of, yeah.
Okay.
Yes.
So it's multi-steps. It's going to be available, right? You just got to remember what you're going to be using. So you got to break down each of the steps. That's the hard part, is breaking down each of the steps. Okay, questions, concerns? Cash, let me show you where you find all of that information on P table. It's so beautiful. Do you guys appreciate P table yet?
I do.
Okay, so remember when it says IE, that stands for ionization energy. So it's the first ionization energy, the energy that it takes to remove a single electron from something. So we were talking about cesium. Here's cesium. The first ionization energy is 375.7. It's a positive value or mole. Okay. So the other thing that we were talking about is the electron affinity. The electron affinity for fluorine is 328 kilojoules. Now, since it's going to be accepting it, in this case, it's going to have a negative value. Okay. So let me pull that back up. Okay. Questions? Concerns? Cash?
How does it go from 1/2 F2 to just F?
Okay. So because 1/2 F2 is, you're saying like it's a half a molecule.
So it's just,
And so, and this is F2. So you're actually just breaking up and you're just keeping the F, one of the F. So you're breaking that bond and just keeping one of the Fs. Does that make sense?
yeah, I just didn't know how to do math.
Yeah. Don't worry about it. It catches me. It took me a while to really grasp this because it's a puzzle, right? You have to figure out each of the steps. Okay, so I have a solid, then I have to go to a gas, and then I can use the ionization, right? So that's just going from the ionization energy is going this guy to C+. So that means that there's electrons that's just hanging out for it to be accepted. So then we go from this guy, make it a box. Maybe I should do a different color. Nobody's colorblind, right? Oh, we'll go from this guy to this guy. And that's what this represents. Okay.
And D is dissociation?
D is dissociation, yes.
Okay.
Yep. And then EA is electron affinity. So that's going from this guy to this guy here. Because it's accepting that electron that had just been kicking around, one that this guy gave up. It accepts that now. And then we're going to go from these guys being separate from each other, coming together. And that's what this is. Okay?
Okay.
Okay. And so if we want the full equation, if we were saying we started from here and we're going from here, all you would do is calculate all of these together, and that's going to give you this value right here. Okay. So that would be the formation. So you don't have to see all the steps, you just see how much energy is. Does that make sense?
Yes.
Okay, good. Good. Okay. So the next thing that we're going to be talking about is polarization. Okay. So, but I actually want to stop here because I don't want to make your brains explode. Is that okay?
Can you go back to the last slide so I can just like take a picture?
Sure. Oops.
Thank you.
Okay.
I understood everything.
What was that?
I think we were all fine and up to this point.
Up until this point. Okay, so let me tell you what your test is going to cover. So your test is going to cover, we're going to go up to lattice energy. Okay, so you guys are going to get a break on this part. But the next test is going to cover this. The next test is going to be right before our spring break. Okay?
Sounds fair enough.
Okay. So then that way you guys have all the spring break to forget everything that you learned this first half. I'm joking. Okay. So are there any questions? Good.
I did about my lab, about the lab.
Okay.
And
So
I was able to get the data from my sister.
Oh, you were? Okay, so you want to share it?
Yeah.
And tell her I'm going to talk noise about her now. She don't show up anymore. She's too good. Wow. Okay, so is this sunlight or is this
It's just one of the glow sticks.
okay, cool. Okay, so if we look at the intensity, the peaks, right? So, wow, it is really weird though. It has really low. And so if you look at it, this part, all of this here is crap. This is all background, right? So you're getting signal from something else. This is where all your signals are. So what you need to do is you need to have it so that it'll focus in on, let me see if I can draw it. you want it to focus in on this area right here? Because it's picking up all of this stuff, which is all background.
Oh, so this area right here?
Yeah. Which is really weird. Because these are supposed to be your nanometers. So your scale looks like it's also a little off.
I didn't know how to like calibrate it or whatever.
Okay.
The same.
So what you typically do to calibrate it, they'll have you find 2 points, right? Typically. So in this case, you have a red point, and although you have a nice little curve going up, right? So you try to find that center of that red point. So you use this as your red point, and then this here is cyan, right? And so you look at the wavelength for them, and so you use that as your calibration.
Oh, okay.
Okay. And so they'll have like values of, they'll be like B2, G1, and all of that. So that's like blue, green, you know. So
But how would I get it into the Excel to make to graph it
that's
out?
the part that I haven't quite figured out. Everybody's been just copying the data, typing it in.
Okay.
But there should be a way, because they calculate this. There should be a way to export it out. I haven't figured that out yet.
Oh, okay.
I've been playing with it myself to try to figure it out, but I still haven't figured it out myself.
I feel it.
But,
So
because I thought you'd be able to export all of that. So once you have, all you need to do is find the wavelength. And so since this is your glow stick, right?
Yeah.
Look at the colors you have. And you could probably, this is bad, I can show you method, right? You look at the color. Here my drawing. Okay, so we have red, we have green, and we have cyan. So we know that we have everything that's going to be red, green, and cyan. So what I would do, if it were me, when I was struggling a bit, and you have an idea of the intensity. So if you kind of focus in on this part here, you can figure out the intensity of those bands in that area relative to each other. So I'm going to kick you off for a second.
Okay.
And then I'll have you come back on. Actually, thank you. Let me see if I can find this guy. This is a long slides. Been talking and talking and talking. Oops. Okay. Oops. Actually, it was the last one. Chapter 6. Let me open it up. Come on. Yeah, here we go. I put it in here. Here we go. This will work. And I actually put one of these in the lab as well, so you can use the one that's in the lab. So this represents angstroms, right? So these are in angstroms instead of nanometers. And actually, is yours in angstroms or is it in nanometers?
You're not sharing the screen.
Okay. Thank you. Was yours in angstroms or nanometers? Because that's also a factor. So this guy is actually in angstroms instead of nanometers. And so you can see where cyan is at. And it goes, it was like red.
Yeah.
So you basically you were covering this area right here with little to no yellow. That one was kind of gone, but you could see the green, you can see the red, and you can see the cyan.
Oh, okay.
Okay. And so you can kind of use a spectrum to kind of calculate, right?
Okay. Yeah, we just weren't sure how to put it into the Excel.
Yeah. So I thought there was a way, and I've been looking myself. So you would just type it into the Excel.
Okay.
Okay. Okay, can you show yours again? Because I'm curious now, because it might be in angstroms and that might be our difference. No, those are too low for if they were angstroms. So can you click on the lower part, the lower graph, where it gives you the values? Yeah, it's I think you just gotta have to refit it so that it's set between two values, right? And so when you do the calibration, define your calibration point and just select a range. So you see where it says calibrate? On that table below? Yeah. Okay, now you see where it says, read the instructions. It actually says, so align the B2 and the G2 to the corresponding peaks on your calibration. So B2 represents your blue, and then your G2 represents your green. So you would want to try to find where the blue is at. So it goes, this is cyan, and then blue would be following it right here. So it'd be like literally right there. So drag your blue right. Yeah. And so, and then drag your green over to the other side. Okay, right there. So, and I'd actually drag the blue. You can't see where I'm going, can you? I drag the blue here because it's literally, it's right after, which you're not seeing at all. So it'll be literally right after that. Okay. And then follow the instructions after that. So go ahead and hit apply. Okay. And take a look at it. Did it do anything? There you go. Okay, so now you've set it up, you set up that range. And so then, although it likes this part here. Scroll down, and if you go, you can set up the region that you want to look at. So limit, you see it, you see where it says limit? Wait, yeah, click there. And then go from start at, yeah, so start at 400 and go to 7, go to like 650. Okay. So now you can, if you want to, you can readjust it, recalibrate. So you can see the blue, the little bluish right here in that area. And then you can see the greenish right here. Although it's pretty much lined up. So you can see your peaks. So you're kind of like right here. So find your highest peak and use that as one of your values. So that's going to represent your cyan. That's going to be that guy. This guy is going to be that green. You're missing, technically, this should be your yellow. This is probably your yellow, which you have very little of. And then you have a lot of your red, which is really like a far red. Not too intense right here. So actually it has its peak right there. So does that help? Are you guys there? Everybody else, you guys got this done already? Piece of cake?
Yeah, I did mine a little differently.
Yeah. Good. Okay. I still haven't figured out, like I said, I haven't figured out a way to export it. I was trying to play with it to see if it would export data, but I thought extract would work, but it doesn't. You know, I tried it. Okay. Questions, concerns, Cash? Jessica,
Yes.
your sister, she had emailed me. Is she still having trouble with it, or did she get it figured out?
Oh, she got it figured out.
Good.
Yeah.
Did you post a practice test yet?
Not yet. I'll be posting it tonight, later on tonight after we finish. Well, later tonight, because I have to finish it.
Oh, okay.
I was gonna see what what curveball I can throw at you. Okay. So if there are any other questions, I'm gonna let you guys go.